All right, so as we review for your mole quiz tomorrow, we're going to be talking about mole conversions. We're going to be talking about molarity. We're going to be talking about percent composition. We're also going to be reviewing empirical formula and molecular formula. So this is going to be pretty quick. I'm going to go through this pretty quick because we just got finished doing this, and this is just in prep for your quiz tomorrow. All right, mole conversions. So if you have to convert from a given mass of something to moles of something, or moles to RPs, which are representative particles, like atoms, ions, all that, etc., then one thing you can do is to remember this chart. And I think this is pretty easy to remember. We have grams on top, then moles, then these representative particles. And the conversions are a couple things you want to remember. When you're converting 2 moles, so the arrow is going to the middle, it's always divided by. Okay, we always divide to go to moles. That's the first thing. And so obviously we multiply to go away from moles. You see that? So that's the first thing you want to remember. And the other thing is the conversion factors between grams and moles is pretty straightforward. It's simply grams per mole of whatever element or compound is in question. So if it's carbon, right? If you have 3.7 grams of carbon, and you want to know how many moles, moles, well, you do 3.7 grams divided by the grams per mole of carbon from the periodic table, which is 12.011 grams per mole. And so you get roughly, just over a quarter here, right? 30% maybe, or whatever, 0.3 moles or whatever it is. So that's your calculation. That's the divide by grams per mole. Okay. Now going from, so it's obviously the same over here too. If you're going away from moles to grams, you multiply by grams per mole. Okay. Because think about unit analysis. If you have moles times grams per mole, then the moles cancel out and you're left with grams. So that's kind of why we do it that way. Converting between moles and representative particles is Avogadro's number. That's 6.02 times 10 to the 23rd power. And that's on both sides there. Going 2 moles, you divide. So if you've got 6.02 times 10 to the 23rd atoms of carbon, and you want to know how many moles that is, well, you divide that by 6.02 times 10 to the 23rd, and that will equal exactly 1. Okay, which makes sense. All right, any questions about the conversion chart? Yep.
Sorry, could you, I know there's atoms, ions, etc.
Mm-hmm.
Give an example of that, because I'm completely
Yeah.
blanking.
Yeah, sure. So I mean, if you have, so the representative particles, if you have, so if I say we have 7.2 times 10 to the 24 atoms of carbon, okay, equals how many moles of carbon? That's a kind of question. So a representative particle would be atoms of an element, or it would be ions. If they were charged ions, it would be ions. So individual small particles like that, or even molecules, right, of water. The other one is formula units that I don't have on here that you don't see very often, but if it's an ionic compound, sometimes they'll refer to them as formula units because they're in this repeated lattice pattern. So it's like one complete unit that's connected in this 3-dimensional lattice pattern. So it's not a separate molecule floating around for some of those ionics. But so atoms, ions, molecules, formula units, that sort of thing. So in this case, again, we would divide by Avogadro's number. And let's see what we would get there. So make sure you use your times 10 to the power of your scientific notation button here. So 7.2 times 10 to the power of 24 divided by 6.02 times 10 to the 23. So we'd have 11.96 with 2 sig figs, I guess. 11 point, well, you have to go 12.0 with sig figs, let's say. So 11.96 actually goes to 12 12 moles. Okay, does that make sense? Any other questions about that first part? All right, molarity, a bit of an extension of that. Molarity is concentration. So this is another kind of a word for concentration of something. And it's the amount of substance per volume of solution. So this liters would be the volume of the total solution. So if you have, let's say, you have some carbon, some graphite or something, you have 12 moles of it, and you're dissolving that into 1 liter of total solution. So that would be 12 moles per liter, or 12 molar. The symbol is capital M. You say it as molar. So this example here, 7 capital M, that's 7 molar, means 7 moles per liter of whatever substance you have. So if we had 20.7 liters of 7 moles per liter NaCl, you'd probably understand that we would have 7 times 20.7, and that's how many moles we'd have. If we have 7 moles in 1 liter, you have 7 times 20.7 moles in 20.7 liters. And again, the unit analysis is pretty slick to know when to multiply or divide. So here we would multiply to get rid of the liter symbol, right? The liter unit, and we'd be left with moles. So molarity, concentration, it's moles per liter. You'll have to pay attention to volumes in milliliters maybe, right? If it's 750 milliliters, that's equal to 0.75 liters. All right, so divide by 1,000 to get liters. So you might have to make that conversion first. Remember that?
Milliliters is the same as centimeter cubed?
Yep. The other thing too, in the textbook you're using and in other places, centimeter cubed is the same as milliliters, and decimeters cubed is the same as liters. So that is something you might want to remember. Good. Any other questions? About molarity? All right. Percent composition we also just got finished doing, and it's basically the percent of each element in a compound, and that's percent by mass. Okay, it's percent by mass. So it's not by moles, it's by mass. So if I have CH4, okay, the mass of, let's say, 1 unit of CH4, if we're talking about grams, we're talking about 1 mole of CH4. So 1 sort of unit or 1 mole of CH4 would be 1 times 12.011, that's the grams for carbon, and then 4 times the 1.00794, that's the grams for hydrogen. And so we would have a total here of about, 16 or so grams. And then to find the percent composition, you take the mass of each and you divide it by the total. So the total grams per mole for carbon exactly is 16.04276. The mass of each element then, that's the individual kind of portion of that particle there, of that compound. So carbon, there's 1 carbon, so we'll use 1 times the mass, right? 12.0011. Divide that by the total, and then because it's a percent, we multiply by 100 to get the percent carbon, and we'll do similar for hydrogen. There are 4 hydrogens, so it's 4 times the mass of 1 hydrogen, which is 4.03176 divided by the total, and then we'll get percent there as well. So let's do hydrogen first. I have that up here. So that's divided by 16.04276. And then if you want to do times 100, just move the decimal place over, obviously, but 25.1% of that is carbon. Oops, that was this one, 25.1%, yeah. That's for hydrogen, right? Sorry?
74.9.
Okay, yeah, and then, yeah, so 74.9% then would be this one if you did that calculation right. So 12 out of 16, roughly 75%. Yeah. And this should add up to 100. If you're rounding, it might not exactly, but we're gonna, that should add up to pretty close to 100% there. Okay, any questions there? Percent composition is by mass, so remember that. Last couple things, empirical formula, we just got finished learning about this. So the lowest, simplest ratio of moles or atoms of an element in a compound. So if you have a formula like this, that is not empirical, the empirical formula, because the empirical formula would be represented by the lowest ratio of all of these subscript numbers here. So we could divide each of those by 2, and that would be C5H7O4. That would be technically the empirical formula. This might be the exact formula of the actual molecule. In that case, it would be molecular formula. So I'll just move to a molecular formula here now. A molecular formula is often a multiple of an empirical formula, almost always. So if you think about this one that we just stated here, if this is the empirical formula, it might be double. All of these numbers might be the actual formula. It could be double or it could be triple. Okay, something like that. So it's a multiple of the empirical formula. And how we find that, how we find out what the molecular formula is we usually first have to find the empirical formula by whatever means you did when we were studying empirical formula. So I won't go all into that right now. But you'd find the empirical formula, and then you'd use the mass of the actual molecule, and usually that's given in the question. Okay, they'll say, hey, the mass is this much. So then what you do is you divide that by the mass of the empirical formula, just the base unit there. And then whatever that number is, that would be the ratio or the multiple that you would multiply by each subscript in the formula. So an example I'll just go over real quick here. If we had an empirical formula of HO, H1 and an O1, and the molecular mass of this actual compound would be 34 grams per 1 mole, then what you would do is you would add up hydrogen plus oxygen, like I did over here, and you would get 17 grams. That's the mass of the empirical formula. So the mass of the actual molecule is 34, so 34 divided by 17 is 2. That becomes your ratio. And so each one of these subscripts here, well, 1 and a 1, you multiply those by 2, and it becomes H2O2, which is hydrogen peroxide. Okay. And we just got finished doing that, I think, yesterday, so it should be fresh in your mind there. But yeah, question?
Will the molecular mass be given to us, like the actual?
Yeah, in this case, you would be given the actual, molecule mass. You bet. Yeah. I mean, could this question kind of be rearranged so that you have to find the actual molecular mass? Well, sure. They could say, here's the molecular formula, and here's the mass of the empirical formula. Find out what that ratio is, or find, they could ask you kind of for a different thing here, but this type of question, that's what it'll look like. All right, so these 4 or 5 things you'll be tested on a quiz tomorrow.